This problem involves manipulating an array int list in which we're going to have to rearrange values in the middle of the list. We're asked to write a method called collapse that collapses a list of integers by replacing each successive pair with the sum of the pair. So for example, in this list, the first two numbers 1 and 2 are replaced by the sum 3. Then 3 and 4 is replaced by the sum of those two, which is 7, and 5 and 6 is replaced by 11, which is the sum of those two numbers. They won't always be sequential integers like this. For example, in this case, we would add the 8 and the minus 3 and collapse that pair into their sum, which is a 5. The statement also says if the list stores an odd number of elements, then the final element is not collapsed. So for example, if we have 1, 2, 3, 4, 5, the 1 and 2 are collapsed into a 3, the 3 and 4 are collapsed into a 7, and this extra number 5 at the end is not collapsed. There might be as few as just one number in the list, in which case there's no collapsing at all, or there might be an empty list. I've set up a JGrasp file that has each of these test cases. I'm using the array initializer syntax here to specify the sequence of numbers to use, and then I have a little testing method here that constructs an array int list, uses a for each loop to add all the data from the array into the array int list, and then it reports the values in the list before and after it makes a call on the collapse method that we're supposed to write. So this is our task, is to add a brand new method to ArrayIntList called collapse that will do this collapsing operation. I have a copy here of the ArrayIntList class. We have its fields, the constant. Here are the constructors. So we can go ahead and scoot down here and introduce a brand new method here. The collapse method is an action-oriented method. It doesn't return anything, so it would be a void return. Collapse is the name of the method and doesn't take any parameters. So our task is to fill in the details here. Now remember that we have this array called element data that stores the different elements of the list, and then a size variable that tells us how much of the array is currently in use. Now if we take a look at the original problem statement, we basically want to come up with a number here that involves a sum of two others, a number here that involves a sum of these two numbers here, a number here that involves a sum of these two numbers. So we want to have a loop that constructs a sequence of numbers, and the number of numbers that we're going to get is half the original number of numbers. So if there were 6 numbers in the list originally, now we're going to have 3. So we could have a for loop here where we would say for int I starting at 0, I less than, well, our normal loop would say I less than size with an I++, but this is a case where, as I said, if we had, say, 6 things, we want to end up with 3 in the list. If we had 100 things, we'd want to end up with 50 and so forth. In general, we're going to end up with size over 2 number of values that we want to be finding. Those are the collapsed numbers that are equal to the sum of a certain pair. So what we want to do is to set element data of I to be the sum of 2 other numbers. So we want to set it to something plus something, where those two somethings are the pair of values that we're collapsing. So let's think about that for a second. When we're trying to figure out a value of the 0th element, we end up wanting indexes 0 and 1. When we want element 1, then we're dealing over here with indexes 2 and 3. And when we're trying to get element 2 of this list, the indexes over here would be 4 and 5. I don't know if you quite saw the pattern there, but basically, for example, in that case where we had an index of 2, the very first number that we want to be including in our add is the value that's at index 4. In other words, an index that's twice the original. So what we can do over here, we know that this first question mark is basically going to be element data of twice that I, so 2 times I. And that's, the different ways of trying to figure that out. It's not terribly surprising that what we're doing is we're taking values from the list where we're going to take 2 at a time. So it's not surprising that the ith value that we're trying to come up with is related to the 2 times ith value of what we had originally. And then what's the other value that we want to add in there? Well, it's the one that comes right after it. So the other value becomes element data of 2 times I plus 1. So that's the one just to the right of it. So that's kind of the way that we get those individual values. We can go ahead and compile this version of the code, make sure that we haven't made any errors here. We can come back over to our client code, and let's go ahead and compile it. And then we can try running it to see what kind of results we're getting for this version of the method. And what we end up getting is that in this list 1, 2, 3, 4, 5, 6, we do end up with a 3, which is the 1 plus the 2. We end up with a 7, which is the 3 plus the 4. And we end up with an 11, which is the 5 plus the 6. So that's very good. We've actually managed to come up with the first 3 values that we want in our collapsed list. But we also have values 4, 5, 6. So we have these leftover values here that we get because we forgot something in our solution. We're overwriting this array. We're kind of overwriting the old values here by giving a brand new set of values that we want to store here. But in the end, we end up with half as many values as we had before. So the thing that we forgot to do over here is we forgot to reset the value of size. So not only do we have to do this, but we also have to deal with the fact that the size now should be the old size over 2, that we have half as many things as we had before. Otherwise, we end up with these extra values at the end here. So we can recompile this version of the code, come back over to the client code, and let's try running it again to see what we get. And in this case, what we end up with is that 1, 2, 3, 4, 5, 6 is being collapsed into the 3, 7, 11, which is what we wanted. This list here is supposed to be collapsed 5, 21, 51, minus 5. If we take a look over here, 5, 21, 51, minus 5. So that's working. This list was supposed to be collapsed into a 20, which it is. And then we have this list 1, 2, 3, 4, 5. Now it's supposed to be collapsed into 3, 7, 5. And the 45 is supposed to be collapsed into 45. So we've got a pretty good answer here. It's giving us the right answers when we have an even number of elements in the list. But it's giving us the wrong answer when we have those stray extra values at the end. So this properly collapsed the first 4 values of the list into 2, but now we've got an extra value there that we didn't account for. So that becomes a special case that we're going to have to write some code for. And there's several ways to do it, but one way that's kind of a straightforward way of being very explicit is we can have an if-else that says exactly what to do in the 2 different cases. So what if the original size, mod 2, is an even number? So that's the case that we found is working already. Then we would want to set size to be size divided by 2. If it's an even number, we just want to cut it in half. So that's the case that we've already done. Else, we want to handle this case, and this would be size is odd. That's the case that we're dealing with here. We haven't yet handled that particular case. So in that case, we had this extra value in the end that wasn't being collapsed. So in the case of the 1, 2, 3, 4, this value that's at the very end has to be copied into our list. So we have to kind of bring that value into that particular spot there. So we want to set element data sub something to be the last value of the original sequence of values. Well, the last value of the original sequence of values is going to be stored at element data of size minus 1. Remember, with the zero-based indexing, the last element that's going to have something in it is the size minus 1 value. So that's the way of kind of referring to that final value of the original list. Where would it go? Well, we've set some values here for all of the i's between 0 and being strictly less than the size over 2. So the highest I that we set here inside of our for loop was the I that was just under size divided by 2. So the next I, kind of the next spot that would be available for us to store something there, would be size over 2. something exactly equal to size over 2. This loop was dealing with all the i's that were strictly less than size over 2. So the next one is size over 2 itself. And then there's also the case of, the issue of setting the size in this case. And size over 2 is almost the right answer. But if you think about that case, for example, where there were 5 values to begin with, if there are 5 to begin with, 5 divided by 2 gives you 2, and we have 3 values that we wanted to end up with. Suppose there'd been 11 in the original list. Then the first 10 will be collapsed. And so 11 divided by 2 gives us 5. There are 5 things that come from collapsing, but there's one extra one. And in each of these odd cases, there's one extra thing to be added to the list. So that's kind of a little tricky thing, is that the size computation is slightly different. We could come up with a single line of code here that did clever things, with adding a 1 before we divide, for example, or using the mod 2 as something that we might add in. So there are other ways of trying to get this same value here, but it's not bad to have this if-else that kind of says we're using the one equation for evens and the other equation for odds. So let's go ahead and compile this version, go back to the client code, and let's run this version of the code. And what we find now is that we're getting the same collapsing we had before on our lists of even length, but now we're properly collapsing this list of odd length where the 5 is being included. The one element list is giving the right answer, and the empty list is not a problem for us. So we have properly come up with the answers that were included here in this table of what we were supposed to be doing in these different cases. And so that turns out to be our solution to this particular problem.